Hi everyone, this is Bala. I'm the CTO and the co-founder of Verifoxx. I'm here to present our research work regarding cWAMR, which is capability-based WebAssembly micro runtime. Before we get into the cWAMR part of it, I would like to give a brief intro and a background of like why we looked into this particular part of the research program initiative and what is the background regarding our product that led to this particular part of it. At Verifoxx, we build a universal layer, which is privacy enhancing technology based universal layer for data collaboration among B2B and B2B2C customers. So this is for enabling meaningful insights on data, sharing insights on your data without having to actually share the data. That's the core. That's the core product, that the core layer that we are actually building, which is a data and a platform agnostic way. During that particular process, this incorporates a lot of privacy enhancing technologies, and one of them also uses the trusted execution environments, or in other words, the enclaves, which is like there are multiple types of enclaves that is actually available. Intel SGX is the most popular one, but you have other AMD, AWS Nitros, and then like a containerized versions of certain enclaves are also available. There were certain limitations while using enclaves, and there were a lot of vulnerabilities and data leaks that is actually proven and that has actually been reported. So in order to make the platform agnostic, we started looking into the WebAssembly micro runtime, mostly because we also wanted to be cross-cloud compatible. So in that case, like when you write your function a code and that can be deployed across multiple environments, WebAssembly was a more attractive option. While we were working in WebAssembly, we started exploring the options, which in the next slides I'll be going through, like what are the limitations of WebAssembly, how exactly these particular vulnerabilities are still existent, the ones that we are looking in terms of data privacy leaks that happens in the WebAssembly part, and how we came across this CHERI platform, which is being developed by the researchers in the University of Cambridge, which is probably close to a decade now. And now this is very close to commercialization at this point in time. Probably in the next couple of years, this new hardware will be commercialized, made widely available along with Intel Arm and the RISC architectures part of it. So first, what is WebAssembly? So WebAssembly is like, so imagine like you have a high level language like C, C++, Rust and Go. You can write your functions in your high level languages, but in order to deploy this particular thing in any target, any platform that you have, and in fact, compile it and deploy it once, have your binary. That is where WebAssembly came into picture. So you can compile once, compile this particular high-level language into a binary or a low-level binary instruction format, which is also the bytecode format out there. And you can start deploying across different platforms at once. You don't have to recompile or rebuild any of these particular modules. The main reason this WebAssembly probably in the last decade has gained too much of prominence here is one is the speed of execution, because you're converting this particular thing into a bytecode, so it is near the machine code level format, so that the execution is as near as the runtime or as near as the machine code runtime. The second part is it's very lightweight. It seems to provide a very simple memory safety feature. It doesn't have complex details regarding it, which we will see in the memory model, how it actually is built. And the most important thing is portability. As I said, you compile once, build a WASM module, and then like you can deploy it in any target, any platform, anywhere you want. You can even store these particular binaries and start like provisioning into the different multi-tenant environments. But the downside somewhere is like in terms of like your debugging facilities or like doing some insights, it's slightly tricky because it's already in the bytecode format. So the profiling and the ecosystem support for this WebAssembly has been developing the last 4 or 5 years for instrumentations and other performances that is happening. For us, this WebAssembly, converting our algorithms into the WebAssembly format was one of the crucial aspect where we had our pets, some related algorithms. We work on finite field state commitments. So for us to extract these particular state commitments, compile those particular algorithms and convert it into bytecode and start deploying across edge as well as cloud environments, WebAssembly proved to be one of an interesting approach. So this is just like a superficial overview of how exactly a WebAssembly program will be, a WebAssembly module will be constructed. At the top level is your module, which is basically performing the function that you are going to intend or the one that you have intended for. And then it is simply broken down into these four different concepts of it. Functions are the individual, like as the name states, these are the individual functions, the work those particular functions that are intended to do. And then there is a table that has the indexes of all these particular functions, where exactly these functions are allocated. Because as we are going to see, the WebAssembly is completely based on a linear memory model. So if you have to access a particular function, it is just an offset from your starting point where the module starts. So the function table are these indirect branches or references to your functions. Memory is actually the linear memory model. We will go a bit deeper into this particular aspect in the coming slides and how the data structure is. And finally, the exports part of it. The exports is nothing but like if you want to export some part of your functionalities that is part of this particular function or module into another module so that you can provide cross linking or the dynamic linking during computation, that is where you will do the exports part. The WebAssembly is a very simple format compared to other high-level languages. It supports only four value types, out of which is 32-bit and a 64-bit representations and integer and floating point. That's it. Any other any other data structure representation such as strings or complex objects, you will have to convert it into one of these particular formats and they will be accessed via the memory. That is how simple and precise the WebAssembly was constructed. And as I said, when it comes to the memory model, uh, it is a very simple stack-based virtual machine. That is a WASM. That's your WebAssembly part of it. So every operation is nothing but a simple push or a pop operation on the stack. You have a separate stack for your functions, like your function frames. That's your operand stack. You have a separate stack for your data, part of it where the variables are being stored. But irrespective of the different stacks that we're talking about, the frames or the data variables, whatever being pushed, it's a simple stack operation. You push in and you pop out. And at this point in time, the linear memory model doesn't have any built-in garbage collections or any other object level programming or the OOPS concept that we talk in certain high level languages. This is the reason why the way it is constructed, the memory model is constructed, and how the bytecode is actually being pushed here on top of it is what makes or what made WASM highly performant or near to the machine code runtime part of it. But now, what happened with respect to this WebAssembly, despite the simpler model? What were the vulnerabilities that we found, that was actually found, and that even we had to encounter? Is the three basic things, the one that we have seen in most of the other parts of the target systems too. One is the buffer overflow, stack overflow, heap metadata corruption, basically the memory related bugs. And especially coming from a privacy enhancing technologies side where the data sensitivity is crucial, you do not want the data that you're processing inside these confidential environments to leak into the host environment or any attack vector from the host able to sniff or do a side channel attack on these memory or the stack part of it that is being allocated to your WASM binary. The two, like there is a lot of papers, interesting papers that has been published regarding vulnerabilities that is present in WebAssembly. I think one of the interesting papers is the pitfalls of WebAssembly. Um, the two root causes that they identify is because of the unmanaged call stack and the statically linked allocators. That indirectly also leads to the third, which is the security related APIs, how it exactly it talks about. So looking a bit deeper into what exactly these vulnerabilities or what exactly these things causes. So when WebAssembly comes into the picture, when you're running some program inside a WebAssembly, the runtime where it is these modules are being executed, they when you're allocating, when you're pushing something onto the stack, your variable or your function frames, when you're pushing, it does not do any memory bounds check. So basically, every operation that you're pushing here is handled via stack pointers. So, and and the minute when I say pointers, we all know how pointers can be manipulated or how vulnerable pointers are. So the runtime doesn't do any um, memory bounds check when it is being pushed into these operand stack. The operating system actually assumes that this particular thing operation that the stack operations is not going to affect any other part of the stack. It's not going to overflow. So it is like an optimal effort. So only the underlying CPU will have to take care of these particular things. The runtime doesn't have provisions for the memory part of it. And during this part, so what can happen is when you are injecting some attack codes, it can overwrite the adjacent parts of the linear memory that was allocated within this particular module, which is your buffer overflow, or in some cases, or in many other cases, it can actually go to the next adjacent memory, which is probably part of another WASM module that can lead to the entire stack overflow part. And it can start corrupting if these bounds are being invalidated. For example, the meltdown attack, where the bounds are completely overwritten because of some malicious code injection. It can also get into the kernel memory. That is it can get into the host operating system. So that is one of the major memory leaks that's happening in the WebAssembly. And the other one is the statically linked allocators. So this is again like when you're initializing a module, you're allocating a particular part of the linear memory. So you're allocating, like you're doing a region of memory that is being allocated. And WebAssembly, because of its performance, so that it has to be quick and far performant, close to the machine code, what it does is like it has statically linked allocators, which means at the compile time itself, it will, when it sees a particular function that has to execute or when a particular stack frame that will be executed in the bytecode format, the memories are already pre-allocated at the compile time itself, because this will also help for other libraries to instrument or profile, start understanding the performance of the WebAssembly. So that is the reason why they have a lot of statically linked allocators. If you start using dynamically linked allocators, you will have to reference external libraries, which can, in many cases, increase the file size. And that is the reason why I think the main concept of while using the WebAssembly is because of its compact size and the compact size of the modules that you want to deploy. That is the reason why the dynamically linked allocators in most cases are not preferred, as the statically linked allocators are used, so that like we try to give the allocations beforehand we start profiling it. This sometimes we use some unstandard libraries, and depending on the runtimes that we use, they might use a very lightweight, not completely tested allocators. And this sometimes cause the memory heap corruption part of it. So these are the two important things that leads into the security related APIs. So even if you have a WebAssembly module that is running inside a runtime, it obviously has to interface. So it has to probably access the file system to get some data, some databases on the host operating system. It might have to talk through a network. It has to open a socket connection and interface with an incoming request to serve or to trigger this particular module that is happening. Dynamic linking is another thing. So which is like cross module connections where you have exported another module and you have to borrow certain functions. So intra-module computations, that is going to happen. Because of the weak unmanaged call stack and the memory allocations, even these operations can get affected. So if your memory is compromised and if your code, if the stack pointer has been violated, it can go and correct the file system in the host. It can start accepting malicious requests on the network socket from the external APIs and start corrupting the entire operating system or the entire execution environment. So these related APIs, these security violations were also happening with respect to WebAssembly. These are well documented vulnerabilities related to it. So that is when in the last, as I said, in the last 4 or 5 years, many WebAssembly runtimes started evolving. Um, a runtime is basically nothing but like, so WebAssembly in the beginning stages, like a decade before, it was mainly used for the browsers, like even the Google Earth right now uses WebAssembly. The main reason why WebAssembly, again, in terms of the performance, they were using for font processing, graphic vector rendering. So those were the things that was like very easy with respect to the machine code level and very faster, so that it has like a good turnaround times. In the last few years, it has migrated not only from browsers, but into a standalone runtimes. That's why you start seeing the terminologies like function as a service, these kind of things that have started coming up with respect to the terminologies. So the runtimes these days, this is again a language agnostic. You can deploy it in any target platform from Intel Arc, Intel Arm to RISC, like the edge operated devices. These runtimes again support interpreters, just-in-time compilation, AoT. AoT is kind of the most preferred in many cases because again, it helps you to optimize quite a few of your library codes and your details. But again, the statically linked allocators and the other problems that we saw starts coming in. When these WebAssembly started evolving, they started incorporating something called the software-based memory bounds check because they didn't want this particular problem to happen. So at the software level, this memory bounds check started happening. What were the problems regarding this particular memory safety checks that was happening because of the software related things? There were the two approaches, most commonly known approaches, the mprotect and the user fault. This is nothing but like when you're allocating a memory to a WebAssembly runtime during the compilation stage, you allocate a big chunk of memories like a stack array for that particular module and with specific area for your operations. The rest of them probably if the needs required, because it's just a stack machine, it has to grow in size. So the adjacent regions of the memory based on the software checks, whether it is permitted or whether it is allowed or not, will be allocated back. Two things is like sometimes you will have to allocate a large amount of memory without knowing what exactly is the requirement of the program because now you're doing a statically allocation. And second thing is this mprotect, how it happens is though we are saying it's a linear memory model, it comes from the underlying OS. So that's actually a virtual memory that is being mapped into each of these WebAssembly runtimes and the modules that are actually running inside it. So the structure of the underlying operating system is nothing but like a binary tree. So whenever an mprotect, whenever a stack pointer is trying to access some part of the memory, when a bounce check, memory bounce check is happening, or it is requesting for additional memory during the operation, this mprotect is going to create a trap, a signal that will lock the binary tree. It locks the binary tree, it does the memory protection, it does the memory bounds validation. And once it does that particular thing, and if it is finding this particular has the privileges or the permissions to do it, it allocates and then only it releases the lock. This started giving like very high performance bottlenecks, especially in multi-tenant environments, multi-threaded environments, because now this results in locking of your main core process, and other threads who are executing within the same runtime on different process cannot do any operation at that point in time. There is the other approach that was suggested, which is the user fault FT, which is again a software level. But here, instead of locking the entire binary tree, they convert these particular memory allocation region into pages. And this happens at the user space level rather than at the like the below kernel level. So at the user space, what happens is it just locks that one particular page so that if other threads are operating on different pages, they continue to do so. So this is how the runtime started building protection mechanisms for the memory safety. But still, the research and the practical papers that has been published regarding this suggest that like this started causing performance overhead starting from 50% to up to 650%, which kind of beats the purpose of WebAssembly runtimes. So the software-based checks, the memory bounds to prevent the vulnerabilities, started giving performance bottlenecks. And if you have to avoid the performance bottlenecks and you have to get near runtime machine code, these memory bounds checks were not happening. That resulted in memory vulnerabilities and leaks into the host environment. So this was kind of like the situation that's right now prevalent in the WebAssembly runtimes. Speculative execution is another example where sometimes even with the software checks, if you're executing in order a particular code, nothing happens. WASM is not WASM does not do any out of order execution. WASM is a strictly in order deterministic stack machine. But the machine on which it runs, the host on which it runs, if those CPUs are optimized to perform the speculative execution, WASM will take advantage, and the third parties who are trying to like who the adversaries basically like trying to extract some information, they will make use of these speculative executions to extract data from the caches from the traces that has been left behind because of these injections that is happening. That is where, in the recent years, we started looking into a concept called double sandboxing. There has been quite a few frameworks that is also available for us. So this is nothing but like instead of running directly on WebAssembly runtime, now the runtime is embedded inside an enclave. So on the outside, you have an hardware enclave. On the inside, you have the runtime and where you start running your module. This is a double isolation so that like the host cannot penetrate inside the specified region. At the same time, the WebAssembly runtime cannot inject or like access the host environment. It is confined within the enclave bounds. I think two well-known frameworks that is available is Twine, which uses Intel SGX as the outer sandbox, and the ACTE, which is the AMD SEV that uses, which is the outer sandbox there. Again, but the limitations of the enclave, which we right now we use in our prod and testbed environments. The point with even here is like it still uses pointers inside the enclave. The enclave region can still be corrupted, though it doesn't get into the host. Enclaves are also prone to side channel attacks. That has also been reported. Spectre, meltdown, speculative execution, all those particular things are subject to it. You can't compartmentalize within an enclave because if one module is being affected, it can affect other pages of the enclave memory too. So the memory bugs still remain as it is. Probably it is now restricted within the enclave and still the enclave can be exploited. That is where we started looking with our research project where this paper focuses on, which is the CHERI platform. So as I said, this is the UK government's Digital Security by Design initiative being worked by the University of Cambridge. This is a new hardware architecture that is quite different from the Intel SG or the Intel 86 architecture looking to be commercialized. And our runtime that we have been choosing, the reason why we chose WAMR, which is WebAssembly Micro Runtime, is basically because of the smaller memory footprint that enables our PET modules to be deployed on the edge devices and the edge computing infrastructure nodes. What exactly is CHERI? Like, how did they change this particular architecture? Like, how exactly they've been working on it? So here, what they have done is like now they have removed the concept of pointers. So pointers, which is a 64-bit address, now everything is a capability. A capability, that means now everything is a 128-bit. So that is double the size, how exactly the hardware itself has been constructed. It retains its 64-bit address within the capability, but now you have like two special things called permissions and bounds that is actually attached. Bounds is basically like the limits, the memory limits of which this particular capability is about to address. It cannot grow beyond this particular part of it. And permissions is what operation this particular capability is supposed to perform. It can be accessing a particular file, it can be accessing like an interface or just executing a module. And within that particular thing, whether it has a read permission, write permission, execute, you can very fine-grainedly provision these particular things from the capability. And there is a special bit called sealed capability registers, where if it doesn't say that like you cannot tamper with this capability, but if you tamper with this capability, this sealed register, which is a part of the hardware architecture, that particular tag will be removed. So that will be cleared. So if the capability is a valid capability, it will be set to true. But if the capability was tampered with or something happens with the bounds or the permissions, that capability will be cleared, which means an automatic trap will be created and the execution will halt at that particular place itself. This way, they provide compartmentalization. It completely overrides, it completely avoids the memory related issues and it compartmentalizes where that particular error has happened. It doesn't let it propagate. They have a few principles. This is available in their papers. The two important thing is it is monotonic and the provenance validity. Basically, every capability will be derived from the parent capability, which means it will never have permissions greater than the parent capability. If you try to increase the capability of the child, which you cannot, if you try during speculative executions and stuff like that, the capability will become unsealed and the tag will be cleared. So which means it will automatically, that capability will be rendered useless. Even if you have made it violate the permissions and the bounds, you cannot use it to access any part of the memory. It will not be taken, like it will not, the program will not accept such capabilities and it will be rejected. That is how they handle this, they enforce the memory protection part of it. So this is a recent paper because even with speculative execution attacks, they found that even CHERI can be subjected to meltdown attacks. So the reason because when speculating, whatever the computations that you are happening, where you're trying to do is not committed to the pipeline. So that means that you can still extract the traces during that intermediate, that transient period of time, because your final output is not committed to the main pipeline. So what they started doing is like they built this capability speculation contract as a part of the hardware architecture itself. So even if you're doing an out of order execution, that is when you're speculating, it will first make sure the capabilities are being checked even before getting into the pipeline. So you don't have to wait till these particular instructions are made into the pipeline. It will get invalidated. And if something such that happens, the capabilities will be unsealed. So in future, if someone tries to extract the traces, it's an unsealed capability. It won't let you extract any of these particular traces. That's this particular contract talks about. So now coming to the part of the work. So with a combination of our WebAssembly runtime and the CHERI architecture, what we have done with this particular proposal and in the research work that we have done here is now we have ported all these WAMR internals, which is the stack, heap, code memories, everything are now capability bound. So everything has been bound by capabilities within the WAMR runtime. We have altered the WAMR runtime to a cWAMR runtime. So now this can be run inside a CHERI platform. So everything has a managed bound. You cannot increase the permissions or the bounds of these capabilities that you're running inside it. The call stack, which is the function frames that is now being popped into these particular things, are now sealed capabilities. So which means you can't do stack smashing or return oriented programming like those kind of an attacks. It will be strictly restricted to that particular function or that delegation that it is happening. So the linear memory is now completely based on capability. It is the linear memory is capability bound. You cannot increase it or decrease it. So you are allocating a particular part of the memory there. The main part here is like now, while we were talking about the file access, network access, those kind of things. So you have this component called WASI, that is the system interface, how WebAssembly communicates to the external part of the world or the host environment. Now we even modified this particular WASI into a capability-based system interface. So now every call, everything is based on a capability provenance. So like I said, if you're giving some access, if you're requesting your module to access some file or accept an incoming socket connection, your capability will be given a explicit permission, which is again not greater than its parent module. It will be given exactly like you just go and read a particular part of the file. You cannot write or do anything, or you cannot go anything beyond that particular file. You can't even read the adjacent file, which is part of, which might be a few offsets away. That is how every permissions will be provisioned out there. And with this, what we also came up with is like enclaves, you can do attestations. So whether it is a local attestation or a remote attestation, you can first connect to a WebAssembly module that is running inside a CHERI, that is inside the cWAMR. You can first check the validity of that particular capability, whether the tag is still valid, get that attestation report. Only if you're convinced that you're talking to a capability bound runtime, you can open your connection and start interfacing with that particular module, start provisioning your data so that it starts running the data sensitive computations that is happening. That's the kind of remote attestation or local attestation, even if it is between two different modules, we have built on top of these particular things. So on the overall, this is how the WAMR runtime will now look. So you will have compartmentalized multiple modules. Each of them have their memories now bound by capabilities, how they interact with the exported APIs. You can have a verifier, which will do your attestation part of it. And then you have like a capability bound WASI for all these external interfaces like the sockets, access, again, bounded by capabilities. This way, now we have started looking into the WebAssembly component module. So you can distribute your modules across different compartments. Right now, you don't have to rewrite every module every single time or compile it into the same module. You can talk between multiple modules, which are now restricted to certain compartments. And these inter-module communication is basically happening through capability delegation. And when we say capability delegation, we know that it has a provenance, so it cannot exceed its parent's permission. It will be just given the bounds and permission what it has to go and do, and it will return back to the parent module. At this point in time, we are trying to optimize the performance characterization. So again, like it is based on hardware enforcement, we are running some benchmarks on the real world scenarios on these particular traversals and trying to improve the compiler so that like the file size is still minimum. So these are the open source optimizations. But at the company level itself, we are working on a concept called multi-compartment computation, because now with a multi-party computation across different nodes, now we have the compartments that is isolated within the same hardware. So we want to do certain key related, secrets derivation related, and pets related modules that we have been running with commitments to run within the same infrastructure and see if they are still widely isolated and how much performance gains that we get rather than having an MPC based model. That's our ongoing steps regarding this research side of things. And as far as this repository is concerned, this is an open source repository. This is available here made to public. Anyone can can use one of these Morello platforms and start running on it. I'm happy to take any questions. Thank you.